Hey everybody. Today we're talking about confidence intervals for the mean in the situation where the population standard deviation sigma is known to us. Big picture, a level C confidence interval for the population mean is an interval that's constructed using a process that will include the true parameter, mu, the population mean, in a high percentage of the cases, and we call that percentage C. A confidence interval for the population mean has the form mu equals x bar plus or minus e, where x bar is the sample mean, so that's the statistic. It's based on the observations of a finite sample that you actually have access to, and e is the margin of error. So you've got some sample data that you've collected. You can immediately compute x bar. The big deal is to compute e, and so by the end of this vid, we're going to have a formula for that. Now, we are assuming that we know the population standard deviation sigma. In practice, we don't usually know that, so that is a bit of an unrealistic assumption in many cases. So later on, we'll have to think about what we can do in situations where we don't actually know the population standard deviation. Here's an example that we'll keep in mind throughout this vid. Suppose we sample 30 data scientists at random, finding a mean starting salary of x bar is $107,000. We want to construct a level 95% confidence interval for the population mean, the starting salary of all data scientists. And we're going to assume a population standard deviation of sigma equals $8,000. The big tool that we're using here is the central limit theorem. And the central limit theorem says that the sample mean, x bar, in other words, the statistic that we're actually looking at in this study, is approximately normally distributed. And it has the same expected value as the overall population, in other words, as data scientists broadly. The sampling distribution of the sample mean x bar also has standard deviation of sigma divided by the square root of n, where again sigma is the standard deviation for the entire population and n is the sample size. In other words, x bar has the same center as the population but less spread, and it also has a shape, a bell curve, that we know how to work with and compute with very directly. You should keep this picture in mind. So here I've drawn distributions both for the starting salaries of data scientists individually, that's the blue curve here, as well as the sampling distribution of x bar, and that's in orange. So the orange curve is representing the situation where I've gone out and got samples of size 30 many times, and each time I've computed x bar, graphed the density of that. So the central limit theorem says that the distribution of x bar has the same center but less spread than the distribution of x, of individuals. And so visually that means that the orange curve has the same center as the blue curve and is just more narrow. And of course, the larger the sample n you use, the narrower the orange bell curve gets. In other words, the more predictable the sample mean is going to be. The more reliably it's going to be close to the population mean. In any normal distribution, 95% of the outcomes lie within about 1.960 standard deviations of the mean. And this is true for the distribution of x bar, which I've drawn here. So, because we're sampling from a distribution with mean mu and standard deviation sigma, x bar is approximately normally distributed by the central limit theorem, mean mu standard deviation sigma over root n. So, since the standard deviation of x bar is sigma over root n, the distance from mu to either boundary in this picture is 1.960 sigma divided by the square root of n. Said a bit more specifically and a bit more technically, we can phrase what I just said on the previous slide like this. The probability that x bar and mu are within 1.960 sigma over root n of one another is about 95%. And we don't need to worry about that math too much, but this is where the formula for the confidence interval is coming from. In particular, if we solve the inequality in the parentheses on that last slide for mu, we get the formula for a level 95% confidence interval for the population mean mu. Mu equals x bar plus or minus 1.960 sigma divided by the square root of n. So, of course, that sigma divided by the square root of n is familiar to us. That's the standard deviation of x bar that we were looking at a minute ago. Changing the confidence level C changes the number 1.960 in this formula, and we'll look at that in just a moment. In our example, we have x bar equals $107,000, sigma is $8,000, and n equals 30. And so we can pretty much just plug those in to the formula that we just wrote. We do that, we plug in, we simplify, we get 107,000 plus or minus 2863. And so with 95% confidence, the mean starting salary of data scientists is between 107,000 minus 2863 and $107,000 plus 2863. Now, bear in mind that the mean starting salary of all data scientists is not a random variable. That's actually just a number. We just don't know it. So when we say 95% confidence, what we're really meaning is that if we went out and got multiple samples of size 30 and made the same confidence interval over and over and over again, we'd get different results just because the x bar would be different every time. 95% of those intervals would include the true population mean, mu. So just bear in mind the randomity in this statement and the 95% confidence, that's referring to the sampling procedure, not to the parameter mu. So what if we have a confidence level C other than 95%? Well, the procedure is exactly the same. We draw the same bell curve, the distribution of x bar, the sampling distribution of x bar, and we want to capture C% of the area there in the middle. And so we need to find z-scores, call them z star, such that that amount of area is contained between mu minus z times sigma of x bar and mu plus z times sigma of x bar. And we can compute that using the inverse cumulative distribution function of the normal distribution, but in practice we actually don't need to. And the reason is that there's only a few C values, confidence levels, that are in common usage. And so we can just get that critical z-score from a table. 95% is by far the most common. You'll probably end up just knowing that when C is 95%, you use Z star as 1.960. The next two most common are 90% and 99%, and they have critical z-scores of 1.645 and 2.576, respectively. Overall, the formula for a level C confidence interval for the population mean mu, when sigma is known, is x bar plus or minus z star times sigma over root n, where x bar, the sample mean, is your point estimate, and z star, sigma over root n, is the margin of error. Now, a lot of the stuff here is just plug and chug. You have your sample mean from your data, you're assumed to know your population standard deviation, obviously you know your sample size n. So the only thing you have to compute at all is your z star. And in this case, that usually just means referring to this table or one like it, finding your confidence level, and plugging in the corresponding z star.